Ways in which certain United States will create such the ways in which we do that.
Professor Dr. Igor Pasti, a distinguished researcher in material science for energy applications, joins us today to discuss the exciting world of hydrogen technologies. Let's delve into the challenges and advancements in electrocatalysis with Professor Pasti. Welcome.
Thank you. Thank you for the invitation.
For the introduction, can you tell me a little bit about yourself? Who is Igor Pasti?
Okay. Igor Pasti is a professor of electrochemistry at Belgrade University. I'm a material scientist, basically. I got my PhD in not electrochemistry as experimental field, but in electrochemistry as theoretical field. So basically, I was combining quantum chemistry, physics of surfaces, physics of materials with electrochemistry, and I also did my PhD postdoc in that field. But now I'm working on experiment and theory together, and now in our group we're trying to combine these approaches to design new materials for energy conversion, primarily for hydrogen production. About other stuff, I'm also involved in faculty management, working as a vice dean for research for 9 years already. Married and 1 kid.
So you mentioned the materials. Are there any advancements in material science impacting hydrogen technology development?
Yeah, I mean, it's like, for me, it seems like it's a race forever, because it's I like to cite one of the highest cited electrochemists these days. It's Professor Mark Kopper. He said something like, I'm paraphrasing actually, he said electrochemistry was always a promise, and now it's our only hope, because it's really like that. Because when you start reading papers for like 50 years ago, 60 years ago, and then 30 years ago, 20 years ago, you always, and if you focus yourself, for example, hydrogen production, so there is always some materials, new materials, and it's getting better, more efficient, so more stable, depending on in which direction you're looking, perfectly in both directions. But it was always like, oh, maybe we can use it to produce hydrogen. And now with this energy crisis, there is no maybe. So we have to find something that we will use to produce hydrogen, convert energy in new ways and more efficiently, and so on. So it's always like a balance between the price and efficiency. And actually, I like to say that all these scientific breakthroughs and catalytic efficiencies, and it's not stability and so on. It's not measured in liters of hydrogen being produced or days that your catalyst is being stable. Everything is measured in dollars, you know,
Yeah.
or euros.
Yeah.
So it comes to a question: is it economically viable? Is it going to pay off? So I think academia is doing a lot, industry is doing a lot. I'm not sure how much they're communicating and who's ahead.
Yeah.
I think industry knows a little bit more than academia right now. But everything comes to the question if it's going to pay off or not.
But my question would be, is it scalable? Whatever comes out of laboratory, how actually is it scalable in a real world?
It's this scalability is always a problem, you know. We're currently we're doing a project like that. We're scaling up some catalysts, but it works perfectly at the lab scale.
Yeah.
But then, of course, then it's a challenge to make it like 5 by 5 centimeters or 10 by 10 centimeters on 25 by 25. I think this scalability issue is killing most of the stuff that comes out of the lab, because it's really the biggest problem, and you can find, like, I mean, something that looks like a perfect catalyst on a paper, which is active. It looks like it's cheap and so on, but then you realize the synthesis is hugely complicated. You cannot scale it up. You cannot make it big enough, and so on. Or you can make it, but you cannot make it fast enough, and so on. So I think 99.9% of discoveries are basically being built by scalability issues.
And then the rest of it comes to the price.
And the rest of it comes to the price. Yeah, I think in principle, when you try to sell something, there is always a question. If you go to someone who's, you have two options. So you can go to some startup which is like, oh, it's super cool. We want to try this. We want to try that. They don't have money to fund it,
Yeah.
Or you can go to someone who's really big, who has money to fund it, but they say, okay, but we have a solution, we don't need yours because our is still working, and we have to invest all the money to change something that is already working. So it can be difficult.
Can computational tools directly design electrocatalysts optimized for hydrogen evolution?
Yeah, computational tools are really useful. That's something that we do. Of course, there are some limitations, and there are different approaches to using these computational tools in developing new catalytic materials. What I think I think the most important thing is to realize that these computational tools, they have limitations. Because if you look at the interface, if you want to produce hydrogen, for example, by doing alkaline electrolysis, so you have a metal, you have electrolytes on the other side of the interface. So you have molecules, you have ions, you have electrons on one side, you have extreme electric fields. It's very difficult to put this complexity into a model, because this is really complex, and it's extreme. So you have to make some kind of approximations, and when you introduce some kind of approximations, then you introduce also the limitations to the method. But it's what I would like to say is these computational tools, they're time efficient, they're cheap, they're really good guidance, and if you use them with care, I mean with realistically, then they could be really helpful. That's the idea.
We mentioned costs a little bit. How can we significantly reduce costs of electrocatalysts used in hydrogen production?
Well, right now, for example, if you look at the technologies to produce hydrogen, you have this PEM electrolysis, which uses platinum-based catalyst or noble metals. You have alkaline water electrolysis, which is using nickel and nickel-based catalysts. I think the way to reduce the price is, of course, cutting materials, I mean metals, the amount of metals being used, improving their stability. So doing many different things at the same time. And what our experience says, it's if you want to go to really high current densities, because currently we are running, for example, 1 amp per square centimeter. For if you want to go to 2 or 4 or 5, it's not going to be about the catalyst. It's going to be about the electrolytes. So in principle, it's at some point catalyst is not playing that crucial role. We will have to develop new electrolytes, new membranes for the electrolyzers, and so on. So I think depending on where in which current region you're working, you will have different targets. For example, improve catalyst, then improve the catalyst and the electrolyte. At some point, only electrolyte becomes important, and then it's
in that context, how can we ensure that the life cycle of electrocatalysts is longer?
It's, well, I mean, a lot of fundamental research, hopefully. 10 years ago or 15 years ago, the main focus on the catalyst development was on activity. So we were always looking at more active catalysts. But at some point, the community, this electrochemistry, electrocatalyst community realized it's not only activity, it's also very much about stability. Because you can have something really active, which will lose activity in a month, or you can have something which is it's relatively good with relatively good activity, but then it will keep it for 2 years, you know. And it's better than have an initially high activity. So now I think this race, I mean, how to say, activity race switched for stability race.
Yeah.
And now we're at this conference, this regional symposium of electrochemistry. We will have some wonderful lectures on the catalyst stability, and a lot of innovation is invested in investigating these, investigating catalyst stability, some really super cool advanced characterization methods in situ and so on. And when I'm mentioning in situ studies, this might be more talk for a specialized audience, but in principle, I have a feeling. I have a feeling for years already that we are missing something in electrochemistry, you know, because we are always looking at our materials and catalysts outside of the cell. So we do some characterization outside of the cell, then we put it in the cell, and we think, it's the same as in vacuum. It's most likely it's not. So we will have to develop these in situ techniques, in operando techniques, so that we can actually assess the state of the catalyst during the operation when it's producing high amounts of hydrogen. And we will also have to combine like different fields, because I mean, when you're looking at the catalyst, which is active or stable, then you need a material scientist. But then if you have really highly active catalyst, for example, for hydrogen production or oxygen production or whatever, you have a lot of bubbles during the water electrolysis. Then you have to solve the problem of bubbles, which is more like a technical issue, how we will remove these bubbles. But then you can also combine it with material science to make a surface which will detach bubbles easier and so on. So it's really complex. It's not developing catalysts for hydrogen production. It's not only a task for an electrochemist or for material scientists. So it's really like a lot of different areas have to sit together and work together on working on different scales, from nano to micrometers, millimeters, then like a realistic size and so on.
So what exciting areas in material science are most promising in this field?
Right now in hydrogen production?
Yeah.
What I would like to say, it's I always believed in this combination of photovoltaics with what, like green hydrogen, how to say.
Yeah.
But combination of photovoltaics for direct conversion of sunlight into hydrogen. So photoelectrocatalysis or photocatalysis for hydrogen production. We had this wonderful lecture today given by Professor Shmuki. Maybe he will also give an interview for you. And he was talking about a single atom catalyst, which is also it's a super interesting thing. So basically, you have a single atom which is active site, so you don't have nanoparticles anymore. So then it's completely irrelevant if you have some really expensive catalyst like platinum, palladium, rhodium. So you just make single atoms and you irradiate it by light and you produce hydrogen. One of the problems with that is that the efficiency is not that high. If you combine with electrochemical production of hydrogen, these currents, like if you would calculate this photocatalytic hydrogen production rate in terms of current, which would correspond to electrochemical production of hydrogen, it would be really, really low. So there is a lot of space to improve that. But I think at some point I'm really rooting for photo to electro conversion. So that's something which I hope will we'll see in forthcoming years.
About the hydrogen storage, are there any new materials on the horizon that could significantly improve the storage performance?
Hydrogen storage is really
Quite a
big
topic.
issue. Yeah, it's really big issue. You can do it in different ways. You can just put it in a in a steel vessel under pressure. Not the fanciest way to store hydrogen, to be honest. You can store it in solid states with making some hydrates. You can absorb it on graphene and
Yeah.
so there are different ways. To be honest, I was not very interested in that from the very beginnings. Never worked actually in the field of hydrogen storage. But speaking with my colleagues who are in this area, there is still a lot of hope on magnesium hydrate. That it will work and improve it by adding some co-catalyst and so on, reducing the temperature for desorption, improving capacity, cyclability, and so on. So I think, I mean, as we develop methods for producing hydrogen, we will also have to improve the ways of storing hydrogen, and also all the infrastructure which follows. So I'm pretty sure it will be very excited in this field for forthcoming years. Of course, there is also a way to convert hydrogen into ammonia. But then you have, if you have hydrogen and then if you want to make ammonia, then you have to combine it with nitrogen. It's basically Haber-Bosch cycle. And this Haber-Bosch is it's so energy intense. So basically, I mean, there are some estimates that between 3 and 10% of globally produced energy every year is spent just for synthesizing ammonia, just for Haber-Bosch cycle. Haber-Bosch process. And so when you convert hydrogen to ammonia, it's easier to deal with it. I mean, it's easier to transport it. You can use it as you can use it as a fuel and so on. But I just don't understand. I mean, how it can be, how to say, economically feasible, or how then we call it like sustainable. If you make it somehow and this efficiency is low, and then you have to invest a huge amount of energy just to convert it back to ammonia. Yeah. So
you mentioned the conference, and the final question: what is the state of hydrogen research and hopefully production in this area of Europe?
In this area of Europe, I've seen some maps. How to say, when people place this infrastructure for hydrogen and future plans where the pipelines will go, where it's going to be produced, and I got really disappointed, you know, because this part of Bosnia, Serbia, Montenegro, it was gray, so everything went around us, unfortunately. But there are, of course, some efforts to get something on the market. We have some small startups in Bosnia. We have some smart startups in Serbia as well. What I see as a true potential here is this electrochemistry community and material science community, which is well known in the world. So I think we really have potential, but what we need is a lot of investment. Because you cannot do science without proper funding. And I was actually feeling a little bad because there were some colleagues from Germany coming yesterday, and we had this welcome party at the conference, and then they approached us and they said, "Oh, really? I mean, is it true that you get that one person in Serbia, I mean, one researcher gets 1,000 euros per year and has to cover everything like chemicals, equipment, travels, conference fees, and so on? Is it true?" Yeah, it's true. So this is really a small amount of money. And if you want to make something, if the government to make wants us to do something, they have to.
What's with the commercial side of it? Are there any companies who have interest or who would like to fund your activities?
There are, of course, some companies, but they're not local companies. I mean, they're
international,
like big international companies.
Yeah,
and it's possible to do it, but then your product is just leaving. It's not yours anymore. So the point is, what's your aspiration? I mean, what you want to do? Do you want to? I mean, one day, like walking down the street and you see your logo of your startup, which is now international company at the same place in this region, or you see the logo of some huge company, international, and then you just say, "Ah, yeah, my product isn't there. I mean, my discovery is behind this logo." I mean, I would prefer this first option, but it's more difficult version.
Thank you for being my guest.
Thank you for the invitation. I really enjoyed this.